Welcome everyone this evening to the Institute of Astronomy here at the University of Cambridge. My name is Ryan MacDonald. I'm an astronomer working in the department here, studying planets orbiting other stars, exoplanets, to try and figure out what these distant worlds are actually like, and how similar or strange and unique they may be compared to the planets in our own solar system. So yeah, when I was the age of many of you here in the audience today, I would look up at a star in the nighttime sky and wonder, could there be anyone living on the planets orbiting around those stars? But at the time, we didn't even know if there were planets around many of those stars. But nowadays, over the last 25 years, we have discovered over 3,800 planets orbiting other stars, which has completely changed the game in the search for life elsewhere in the universe. So if we want to know where the aliens may be, we should perhaps first start by thinking, what actually is life? What makes you or I different from this table or the ceiling or a rock, for instance? What is life? So I'm going to try and make this a little bit interactive as well. So does anyone have any immediate suggestions? For life here on the Earth, what do we need for something to be alive?
This is ground.
What was that, sorry?
This is ground and biology.
Mm-hmm. So yeah, what makes something biological? What's the difference between a biological life form that's not alive? Yep.
I think for life to be able to thrive on certain planets, there would have to be perfectly correct conditions in the atmosphere and in the soil for plants and life to survive over millions of years. Like
You are absolutely right. Absolutely right. So let's start with a case study. Our own planet, the Earth. And if you look at the Earth from space, you can clearly see that there's something different about this planet. It's very different from the other planets in our solar system. As we zoom closer and closer, we can see that the entire surface of this planet has been modified by the presence of life. We see vast green areas coating our planet. And if you zoom down further, life is in incredible abundance on the surface of the Earth. But life isn't just something that takes up space. It actually modifies a planet as well. In fact, before life, such as plants and trees, arose here on the Earth, almost all of the Earth's atmosphere was composed of carbon dioxide. But nowadays, the Earth's atmosphere is quite different. Does anyone know what the Earth's atmosphere is made of? Which gases? Yeah?
not very sure.
Okay, yeah.
Molecules of water in the air in a compound with other molecules that I can't remember.
But you are right that water vapour is indeed a very important part of the atmosphere. Yeah.
Nitrogen.
Yeah, nitrogen is the main component of our atmosphere, occupying over 75% of the atmosphere. Yeah?
83% nitrogen, I believe. And then it's fairly evenly split between CO2 and oxygen, and then there are some other gases and stuff which make up less than 1%.
So a quite good suggestion. So yeah, it's precisely 78% nitrogen, about 21% oxygen. If the CO2 was actually equal to the oxygen, then the planet would be in an inferno and we wouldn't quite be able to breathe on it. So we're slightly fortunate that CO2 is quite small now. So yeah, the main gases, nitrogen and oxygen. Oxygen being the most important component. Now, one of you mentioned that water is a crucial component, not just of our atmosphere, but also it is vital for life to exist. The majority of our bodies are composed of water. Water provides the liquid medium in which the various reactions that life requires takes place in. So all life that we know on the Earth requires water to exist, and that is crucial. Another important thing that life needs is life needs a source of energy. If you want to pick something up, you have to eat something, you have to consume, you have to gain energy to be able to process and interact with the world around you. So life requires water and it processes energy. But life is also not distinct fundamentally from the laws of physics. Life is just a chemical reaction, much like everything else we see around us. But there is a vast wide array of different chemical reactions that can take place. And life is selective. It doesn't use all of the different chemical elements. In fact, all life on the Earth primarily uses just 6 of the chemical elements: carbon, hydrogen, nitrogen, oxygen, and small amounts of sulfur and phosphorus that I've highlighted here on the periodic table that you might remember from your chemistry classes. So life is highly selective, which is very, very interesting. But if life wants to carry out chemical reactions to conduct its various functions, it can't just do that out in the open. Because if you carry out a chemical reaction here with no container, it will just spread out over the surroundings. So life needs a way to trap the chemistry of life and separate it from its surroundings. So it needs to have a membrane or a wall protecting it from the external environment. And this is something that all life on the Earth, whether it be plant, animal, bacteria, they all have to find a way to trap the reactions inside. But if this was all there was to life, life would just stay the same, which would be very, very boring. Nothing would ever change. Perhaps the most crucial aspect that makes something that is alive different from something that is not alive is that it changes over time. Does anyone know how life actually does this? How does life change? Ooh, yeah.
Natural selection.
Natural selection, absolutely. And the way natural selection works is that all life on the Earth has a special molecule, DNA, deoxyribonucleic acid, that encodes the pattern that differentiates you from me, from monkeys, from dogs, from cats. They all have different DNA. But when DNA makes copies of itself, it's not entirely perfect. Sometimes it makes mistakes. And we call these mistakes mutations. The vast majority of these mutations are incredibly harmful and lead to an organism not surviving, but some of them can give you superpowers, can make you much better able to survive in the world. And it's those mutations, the beneficial mutations, that are ultimately passed on. So everything that I've said here is just true for life on the Earth. If we want to think about life elsewhere in the universe, we need to think how we can generalize this. So there are many, many ways that astronomers have tried to do this. I'm just going to pick one of them that NASA uses, hence called the NASA definition, and seems to work quite well, which is that life is simply a self-sustaining, meaning it keeps itself going, chemical system capable of Darwinian evolution. Notice this doesn't say that life requires water. It doesn't say that it needs to be made of carbon. It doesn't even say it needs to use DNA. All that we need for life is it needs to be able to keep itself going, and it needs to be able to change and evolve over time. And this is perhaps the most general idea that we want to hold on to when looking for life in the universe. So, where have we already looked for life in the universe? How are we getting along with the search for life elsewhere in our universe? So perhaps it's best to start right here in our own solar system, where there are a number of planets that are quite easy to access, along with a number of moons. So in the very early days of the space age, when we were exploring the solar system for the first time with spaceships, Mars was the focus of many of the early missions. Now, the Victorians even were convinced that there were Martians. There were a number of quite prominent astronomers back in the day who were convinced they had seen canals on the surface of Mars that must indicate a highly advanced species living on the surface. But when we arrived at Mars and took close-up photos, we see a very different story. We don't see canals over the surface. We certainly see many systems that look like dry riverbeds. We see giant canyon systems and a number of ancient extinct volcanoes on the surface of Mars. So although the Mars of today may not be that hospitable to life, if you zoom back and turn back the clock, about 4 billion years ago, we have now learned from all the different orbiters and rovers that we've sent to the surface that Mars once would have been a much more hospitable place. We know that bodies of liquid water were stable on Mars for hundreds of millions of years. But what we don't know yet is whether there actually was life on Mars. And that is a question that remains to be addressed. There were early attempts over 40 years ago in the 1970s to try and find signs of life on Mars. Famously, the Viking lander that we see Carl Sagan standing in front of here. The Viking landers landed on Mars. They took samples of the Martian surface, they added nutrients to it, they injected it with water, and they were hoping to see that if there were microbes present in the surface, they would start ingesting these nutrients and start producing gases, such that we could detect those. The results, unfortunately, from the Viking missions were relatively inconclusive, and it remains controversial as to whether the Vikings saw anything that could have potentially been signs of life. And unfortunately, the null results from the Viking landers led to a lot of astronomers and planetary scientists giving up on the search for life on Mars. It was seen as too costly and too unlikely to succeed. But that situation is changing. In just a few years' time, the European Space Agency is going to be sending a new mission to Mars, the first mission to look for life since the Viking missions. And the ExoMars rover, which we're building here right here in the UK, is an incredibly interesting system because instead of just looking at the surface of Mars, it actually has a drill on it that can drill down up to 2 meters beneath the surface. And we believe that if there is life on Mars today, it must be at least that deep to protect it from the radiation from the sun, because unlike the Earth, Mars doesn't have a magnetic field shielding it. So by collecting this sample and analysing it on board, we may be able to find samples indicating life on Mars within just the next few years. So that is Mars, which historically has been one of the most popular places to look for life. But it's not the only place in our solar system where we might find aliens. If we go further out and look at the moons of Jupiter, in particular Europa, one of the moons of Jupiter, it looks like a giant ball of ice, but it's not ice all the way down. We actually know from the various orbiting missions that we have sent to the moons of Jupiter that Europa has an ocean of liquid water a few kilometers beneath its surface. Remember that water, at least on the Earth, is one of the most crucial ingredients required for life. We have even seen evidence of jets coming out of the surface of Europa. So one idea might be to send a spacecraft to fly through one of these jets, collect a sample, and if there is even a single organism down here, it would only take a few thousand years to contaminate the entire sea with bacteria. So it would be very easy to detect in one of these samples signs of alien life. So there are some plans to send missions to conduct reconnaissance on Europa. Europa Clipper is one that NASA is currently working on, that currently is not planned to fly through one of these jets. It's more to take high-resolution photos of the surface to plan future landing sites that may then follow later in the 2020s. So there's one final place within our own solar system that I want to focus on, which is one of the moons of Saturn, which could potentially host a completely strange and exotic type of life, unlike anything we have here on the Earth. We're going to sell this for now. So this is the moon Titan. Before 2004, we didn't really have an idea as to what Titan looked like on its surface. And that is because Titan has an atmosphere which is much thicker than the atmosphere of the Earth. And so just using telescopes, it's not possible to probe all the way down to the surface. But in 2004, the European Space Agency sent a lander. This is a real photograph taken during the landing of Huygens, a probe, onto Titan. And what we found, this is just an artist's concept, is that Titan is the only other body in our solar system with large bodies of liquid on its surface. But this is far too cold to be liquid water. These liquids are hydrocarbons, things like methane, ethane, and propane, that instead of being a gas like they are here on the Earth, they take liquid form. So the question is, could there be some strange exotic biology, not using water, but perhaps using liquids such as ammonia to support its biochemistry in those seas? So there are plans being developed at the moment to potentially send not just a boat, but a submarine to explore the seas of Titan, looking for signs of a completely alien type of life in the seas. If this mission is approved, it likely won't arrive at Saturn until about 2040, because Saturn is a very, very long way away. This Titan submarine will explore the oceans, searching for signs of alien life, and then transport those findings back to the Earth. So everything that I've talked about here is just searches for quite dumb types of life. Simple microorganisms, maybe single-celled or multi-celled, existing on the other planets or moons in our solar system. But the question that I imagine brought most of you here today is about more intelligent life, life that we might have a conversation with. So what about life, advanced life, further out in the universe? Where are these aliens? So let's zoom out from our own solar system to our galaxy, the Milky Way. Here you are, on one tiny, tiny little star, surrounding one of the spiral arms of our galaxy. Just one star out of 400 billion stars. Now, since we have started finding planets orbiting other stars, exoplanets, we have now learnt that the Earth is not actually rare. We have found out that, on average, every star in our galaxy has 2 planets. And planets in the habitable zone are very common. At least 1 in 6 stars similar to our Sun have a planet in the habitable zone. So this potentially means, when you account for all of the stars in our galaxy, we could have more than 100 billion Earth-like planets. Oh, and if we account for the rarer types of stars, the common M-dwarf stars, which are quite cool, then it goes up from 10 billion to 40 billion. So this poses an interesting problem, because our Earth is quite a bit younger than the age of the universe. The Earth is about 4 billion years old, the universe is about 14. So some of these stars have had a lot longer for life to develop on them than on our own planet, the Earth. And if you crunch the sums, you can work out that if you can build an interstellar spacecraft, you can explore the entire galaxy, settling star after star after star, in only 10 million years. So if there are stars that are 4 billion years older than us, and it only takes 10 million years to settle the entire galaxy, why haven't we already found aliens? Like, why don't you go down to the market and you see an alien there, for instance? They've had plenty of time. This is the heart of one of the most crucial enigmas in astronomy today, which we call the Fermi paradox. Simply put, if there are aliens all over the universe, where are they? Why haven't we already seen them? They should already be here. We should see signs of them all over the universe. So something must be going on. Now, astronomers haven't figured out what this answer actually is yet to this paradox. So I'm just going to present you with 10 possible solutions that we are considering. And then I'm hoping we can get into a conversation over the drinks that will be outside as to what you think the answer is. So the first 5 that I'm going to talk about involve aliens existing, but there being various reasons that we can't see them. So perhaps One of the simplest ones is they just don't care about us. They just deliberately avoid the Earth. Because we're very simple, we're not highly advanced. Maybe they see television footage of Trump and they're like, nope, we're not coming over here. Nothing intelligent to say to these people. What if they are talking, but we're too dumb to understand what they're saying? Maybe instead of using radio waves to communicate, they're using high precision, high power laser beams to communicate. Such that they could be chatting, they could have their alien Facebook, and we just can't hear them. Maybe they're stealthy aliens. Maybe they're actually afraid of us. I mean, I would be afraid of us if I'd seen some of the things that we put out on TV. So perhaps they're all just hiding and waiting to see what we do first. This is one of my favorite ideas, called the zoo hypothesis. They're all watching us and they're like, wow, this is the best TV they've ever seen, just watching us. And it would ruin it if they announced that they existed. So we could just be a cosmic zoo and they're all enjoying watching us. An idea that's very popular from science fiction as well, particularly Star Trek, is that what if the aliens have all decided together that we can't interfere with life forms that aren't sufficiently advanced to make a good neighbour, if you will. So they've put up a barricade, if you will, around our solar system and said, no one is allowed to pass this, wait until they fix their problems and then we'll talk to them. So all of those 5 ideas have a problem though, which is that they have to apply to every single alien species in the entire galaxy. If you get even a single alien that decides, well, I'm not going to obey this, I want to go and say hello to the humans, then it's ruined. And you also need to evoke sociological arguments. You need to say every alien society, regardless of how they think, will behave in the exact same way. So these explanations are tricky to believe overall because they have to be very, very general. So what if there simply aren't aliens? Let's think for a moment about all the things that have to go right in order for a planet to actually have life. So let's think about the Earth. What makes the Earth special? There's a huge array of things. If the Earth was too close to the centre of the galaxy, it would be blasted by radiation from the black hole there. If it's too far away, there aren't enough rocks and metals to actually form the Earth. So it has to be at about the right distance away from the centre of our galaxy. You also have the problem that really big stars burn a lot of fuel and don't live long enough for life to evolve. So we need a star similar to our own sun, or slightly less massive. But very, very small stars continually throw out flares that could strip away the atmosphere of a planet. So we're seeing that there's a lot of things that actually have to go right. The habitable zone around our own star has actually moved over time because the sun's output has changed over time as well. So you need a planet that can somehow stay in the habitable zone. We also believe that you need a large moon to stabilize the planet, otherwise it rocks about a lot, which can cause dramatic climate change. A magnetic field we need to protect us. Mars doesn't have a magnetic field, and that has caused problems. And many, many, many more objections that you can come up with. There's a lot of things required. But what if we do manage to overcome those, and we manage to start life? Great. But what do we need to do to take very, very simple organisms and build complexity? So let's start life, let's survive, let's create all the different components, let's build DNA, we might want to have some plants, for instance. We need to create a unit inside the cell to hold the DNA, the nucleus. We need to go from a single cell to a multicellular species. And by the way, on the Earth, this step took over 1 billion years. And as far as we can tell, it only happened once. So what if the probability of a life form going from being single cellular to multicellular is so rare that on average it might take 100 trillion years to take place, and we just got lucky? that could genuinely mean that we could be the only life in our entire galaxy just from overcoming that one step. And there are many, many more steps to get to intelligent life. Okay, but what if intelligent life does arise? Perhaps the intelligent life doesn't build a civilization like our own that can ultimately explore the stars. So there's a lot of things. You've got to make tools, you've got to invent language, you probably can't build a spacecraft if you're just like, ugh, 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 hit, hit, hit. So you need to be able to talk to each other. Fire and learning how to tap into different types of energy to power processes is a vital part of any civilization. And food sometimes helps. You need to be able to take metals out of the ground, extract them from rocks to be able to make metal tools. And there's a lot of things. Oh, and this one I highly recommend. Science is very useful if you want to build spaceships. So even if you just say, for every one of that massive list that we've gone through, that there's 50% chance that life will be able to do it, when you multiply 50% this many times, and there's a lot more reasons I haven't put there, you can actually come up with a probability that is so low that it could mean we're the only life in the entire universe. And perhaps people who are pessimistic, their favourite explanation is maybe most intelligent life just doesn't survive long enough to go into space. We've actually been quite lucky here on the Earth, not blowing ourselves up with nuclear weapons. Personally, I'm a lot more optimistic. I don't think that it's inevitable that life will wipe itself out. And even if it does happen, there are enough planets in our galaxy that I'm sure some life forms will be sensible enough to survive. So the final potential explanation that I want to leave you with is one of my own personal favourites, which kind of combines the previous categories. It allows for alien life to exist and be common, and for us not to see it. Here's the idea. So let's say an advanced life form develops, it survives all the different stages it needs to do, and builds a spaceship. Where might it go? Here's the idea. If the ultimate goal of any civilization is to figure out how the universe works, they'll want to build larger and larger computers. But the problem is, if you want to make a computer highly efficient, you need to cool it down to very low temperatures. But space itself is not the coldest that you can get. It's actually about 3 degrees Celsius warmer than the coldest theoretically possible. So even if you converted the entire Earth into a computer, it wouldn't be perfectly efficient. But aliens might know this, and they will be clever. It turns out, according to Einstein, that if you travel to a black hole and orbit the black hole very close, time actually goes slower for you relative to your surroundings. And you can use this to travel into the future. And in the future, when the universe has expanded, it's almost like a hot air balloon expanding. It gets colder inside as it grows. So the aliens may all be orbiting black holes, traveling to the end of time, where their computers will work more efficiently. So that's my personal idea that I like. But the crucial thing to emphasize is that we don't know the answer to this question. What ultimately I'm hoping to do in my own research is to find signs of life elsewhere in the universe. Because the second we start detecting signs of life, then we will be able to actually start ruling out some of the potential explanations. So I'm hopeful that over the decades to come, we will actually start to figure out parts of this question. So there's plenty more that needs to be done in this area. And I'm hoping that many of you in the audience will join me in this epic quest to try and figure out where the aliens are. So perhaps you will be the ones who will find where the aliens are one day. So thank you very much, and I'm happy to take some questions.